rolling. Okay, then I would like to record, I mean, I have to record it for the Max Planck Institute. So thank you very much for coming. And now I know a little bit of your background, so I will try to keep it as general as possible and maybe not go that much into detail. And I hope you can then go to the resources that, or the sources that I will give then at the end of this lecture, to sort of give you an idea or an introduction on how so where to go to read it. So basically what I want to do in this Ringvorlesung, I mean, I know you come all from sort of a little bit different backgrounds, so machine typing, machine learning and PDEs and algebraic geometry and so on, gauge theory, as Shuhan said. But what I would like to give you is just a general overview of what are sort of the interesting results, and with results I mean interesting in a very broad sense of non-commutative geometry. And in the end, I would also like to go to what applications does it have in regards to physics. Okay, and because in a sense, so there are in physics we have this problem of finding the world formula, as they say, and basically what the thing is that there are different theories, of course. I mean, but what we would like to have is a theory that unifies, in a sense, quantum mechanics with gravity, because we have these two classical fundamental theories of physics that are sort of the fundamental pillars among which physics relies, and which one is gravity, so it has to do with very massive objects that have also a certain speed, and then you have quantum mechanics, which deals with things that are very, very small and on a subatomic level. And we would like to subatomic level, and we would like to connect those two theories, for example, to describe what happens near a black hole and stuff like that. And it is not clear how to do it. Okay, so this is sort of a little bit what differs a physical point of view from the mathematical one, is that we don't know how to do it in the beginning, and right, and now we are trying sort of to to figure this out. Okay, sorry. So in a sense, there are many paths to that. So there's string theory, there is loop quantum gravity, and a lot of paths. I mean, 1.5 hours wouldn't be enough to tell you about all the possible paths that should lead us to a quantum theory of quantum gravity. But one which I followed during my short career up to now is the path of non-commutative geometry, and in particular rigorous deformation quantization. I will explain what this is, but in general I just want to give you an idea of what is non-commutative geometry, what we deal with, what aspects are interesting and can be applied sort of to any modern day mathematics, and then try to convince you in a sense of what the physical motivation is to work with that. So sorry, I'm a bit annoying maybe, but could you tell me if you can see my screen? So just a simple yes from anyone would suffice. So the PDF that I opened.
Yeah, we also see your mouse.
You see the PDF and my mouse?
Yes.
Okay, perfect. Thank you very much. Yeah, so the nice thing about Zoom is that you can also do interesting stuff with it. So here, all right, and spotlight. Okay, so so I will give you first a mathematical teaser, sort of, to non-commutative geometry, as I call it. Sorry. Right. Spotlight. Okay. And right. And so let's start with what is geometry. I mean, I'm sure most of you have a better answer than I have to that, and are pretty much more familiar with that. But in general, what geometry, a fundamental aspect of geometry is the distance function. So you have, these are sort of very nice graphs of different types of universes that we have, right? So if the universe was a flat universe, if the universe was, a hyperbolic one or a spherical one, and so on, these are so we have in general relativity, there is the so-called Friedmann-Robertson-Walker model, and corresponding to that, there are different solutions of how the universe might look like, right? And in general, so the distance function is, you have 2 points, and you want to know the shortest path from P to K. So you have the point P and you have the point Q, and you want to know the shortest distance between these 2 points, okay? Now, the point is, when we want to talk about or define from a physical perspective, when you want to define the theory of quantum gravity, it is somehow ingrained in your mind or intuitively clear that the notion of a point will be missing. And that is due to quantum mechanics. So the question is, what happens to the distance function if the notion of a point is missing? So how would we still give meaning to the word, or to the aspect of, or to the concept of distance? And so the 2 questions that I ask here is, what happens if the notion of a point is missing? And how does one define the notion of a distance in such a setting? And one example how to do that is quantum mechanics. So, in quantum mechanics, sorry, it's not an example. In quantum mechanics, this is exactly what happens. You have, so just to explain to you broadly, you basically, in classical mechanics, you have some particle and it moves, along a certain trajectory with a certain momenta, right? And if you collect the momentas and the coordinates of this particle, they make up what you know in mathematics or in symplectic geometry as the so-called phase space. But in quantum mechanics, you cannot measure with absolute accuracy the momenta and the coordinate of a particle. Thus, you have to work, instead of working on a classical symplectic manifold on a phase space, you work on a Hilbert space. So and quantum mechanics basically is the fundamental theory describing dynamics and interactions on a subatomic level. However, they are in such a way that they are not too, what do we call it? Not too quick. Okay, so yeah, okay, so you see, in quantum mechanics we have in classical mechanics, things cannot become too quick, because if the velocity reaches the point of the speed of light, or is near the speed of light, then our classical concepts break down a little bit. And quantum mechanics takes into account sort of on the physical aspect in a macroscopic level, but just quantum mechanics alone is sort of the classical aspect, so it does not take into account what happens if these subatomic particles move very quickly. For that, then you have relativistic quantum mechanics, which then turns on into relativistic quantum field theory, and that would be the more fundamental theory for that. But in a certain aspect, quantum mechanics describes enough so that we can build a lot of stuff that we use on a daily basis and understand, or misunderstand the world around us. So classically, there is this, there are many pictures that they always draw to you when you, sorry, I just want to mention that as well. So this is more of, I am telling you the story of stuff, and I hope I can go a little bit deeper, but you can interrupt me anytime for any question so that we can also have a discussion. So since that aspect is obviously missing, since we're not, I don't see your faces and we're not physically present. So classically, you have the state space that is given by some symplectic manifold, which we sometimes call the phase space. And in quantum mechanics, this is replaced by the Hilbert space. observables. That means things that I can observe and measure. And they are, well, I mean, in classical mechanics, there isn't even a real difference between those two. In quantum mechanics, there's a whole lot of difference between observables or operators that represent observables and our measurements. But however, in classical mechanics or in classical physics, they are just given by classical functions on this phase space. And in quantum mechanics, they are given by unbounded operators defined on a dense subset of the Hilbert space. So, I mean, since you're all mathematics students, basically, I'm pretty sure you had some introductory course on functional analysis. However, could you, I mean, yeah, I mean, whatever. If there's any question, please don't. So just ask me. Okay, sorry, something's going on right now. Sorry, I'm having a little bit of problem with this thing. Oh, sorry. Sorry, let me stop sharing for a second. And reshare again. Okay. Right. So the constituents, as I call them, in classical physics or classical mechanics, are just some points. And in quantum mechanics, you replace this point aspect with states. Yeah. Now, just an example. I mean, in classical mechanics, you have, let's say, the symplectic manifold given by R2. So you have the coordinates x and p, and you have some function f of x and p that sort of describes the dynamics of this particle. Now, the observable x is identified with the coordinate and p with the momenta. And so, and then you draw these nice phase space diagrams that, you know, tell you in principle, to every point x and p, you know sort of what the particle is doing or where the particle is. I mean, that is sort of the idea of a phase space, and well, it is the cotangent space of the configuration space as well, but that's maybe not that interesting. And in general, I mean, for our aspect, so in general, any choice of generalized coordinates xi define conjugate momenta, okay? So you have xi and pj in the Poisson bracket is equal to delta ij, where I and j goes now from 1 to the dimension of that. Right, and now, so this is the Poisson bracket, and it is defined in a certain way, where it's defined by the derivatives with respect to one coordinate and the derivative with respect to another coordinate, and they fulfill anti-commutativity, so they're anti-commutative. So xi Poisson bracket xi pj is equal to minus Poisson bracket pj xi. They're bilinear, and they fulfill Leibniz, which is also very nice, so, and the Jacobi identity. Okay. Now, in quantum mechanics, the point is you have an analog of that, but in general, and this is in a sense really the heart of quantum mechanics, is that the momenta and the coordinate do not commute. Do not commute. Sorry, let me try to write here something. Yeah. So the point is that you have these two coordinates, right? Or you have these two observables. Now there's a particle moving in some field, okay, around. Now you want to measure those, and the way, I mean, measurements are done, you do a lot of them, so let's say 100, 1,000, and then you take the mean value of that, and then there's an uncertainty also to that. But this uncertainty in classical worldview is just a probability issue, right? While in quantum mechanics, it's ingrained in the theory. So that the uncertainty, so this basically translates to the uncertainty of the coordinate times the uncertainty of the momenta is always greater equal than a certain constant. This is called h bar, which is the Planck constant, which is, it has some certain value, but it is very small, okay? So on a day-to-day level, you don't notice that you cannot put a particle in p equal to 0, and then you know exactly where the x of it is. So then the uncertainty of p is 0. So you don't notice it. But in quantum mechanics, in a sense, there is a restriction to that. And this restriction, I mean, Heisenberg later on went on to do this via matrix algebras, because he realized, okay, matrix algebras are an example of algebras that are non-commuting. Oh yeah, so the commutator of two operators, for you who don't recall it, is basically A, so the commutator of A with B is equal to AB minus BA. Now, I don't know how familiar you are with functional analysis. As I said, please interrupt me anytime you want. So here you have an abstract algebra. Usually, I mean, this algebra is called the, so if you have two elements or three elements, actually, there is also some sort of unit element here. And this unit commutes with all other elements of the algebra. This is so the collection of these three elements is called the Heisenberg group. So you can also have it here, it's the three-dimensional Heisenberg group. You can also have it for many more dimensions, right? And since this is just an algebra and you want to work with it, in a sense, you want to take eigenvalues and uncertainties and expectation values and so on. So things that in the end lead to a measurement that you can, well, that you can compare with other measurements, in a sense, to justify or to verify or falsify your theory. So you need a representation of this algebra. And the representation, I will go into more detail. I will give more rigorous definition of a representation, but basically a representation is you have pi and you have h, where, so it's called, this is called the representation, where h is a Hilbert space and pi is a map from the abstract algebra. So let's call this abstract algebra HA, and pi is a linear map between HI and, oh, well, I called it, well, and the Hilbert space. Well, maybe it's not very good calling it that, but whatever, you know what I mean. So it's basically a representation of the algebra on a Hilbert space. And a faithful representation means that the kernel of this representation is equal to 0. So it's the null space. And so we say, so in order to represent this abstract algebra, we use the Schwarz space, which is sort of a subset of H, which is, let's take the square integrable functions on R, right? And okay, the Schwarz space, for those of you who are not that familiar with it, is just it's a space made out of all C infinity functions that decay fast enough, even if you multiply them by various polynomials of x and derivations. Okay, so you take a function, it's C infinity, you can put on it x of arbitrary polynomial and derivatives, and it still is finite. Okay, that makes the thing, I mean, a classical example for that is basically e to the minus x squared, okay, on R, let's say. That is a very nice Schwarz function. You see, if you differentiate, if you, first of all, it's square integrable, obviously. Second of all, you can always, so the differential and the multiplication with x basically does the same thing, but I mean, you can have here x to the n. So you see, if I derivate e to the minus x squared, I get sort of polynomials of x down, and it basically, you will end up with an expression of xn where n is a multi-index. Okay, and this thing is still, you know, in the supremum finite. Now, the way to represent those algebras is we say x acts as a multiplication operator, and P as a derivation operator. Notice, however, if you work on R, these operators are unbounded operators. And for you who are familiar enough with functional analysis, pretty much know that that unbounded operators, well, are a mess to deal with. But I mean, the famous quantum physicist Haag once said that it is an unfortunate fact of life that we have to deal with unbounded operators. But nevertheless, we have to. That is exactly the point. Because I mean, you have to take more care of their domain, and they don't have, for example, as in the case of bounded operators, a supremum norm defined to them, and so on and so forth. Now,
excuse me,
yes,
I would have a short question.
Yes.
So the representation, does it take values in H, so in the Hilbert space, or in the operators on the Hilbert space? Because I mean, we kind of define x hat of phi. So yes. Like yes. It is a function on the Hilbert space again, right? Yeah. Or on the Schwarz space.
On the Hilbert space. So you represent it as, well, I mean,
so what I
should have written here is the representation of this operator is as a multiplication operator on phi of x. But
so, but what is the range space then of the representation?
Right. I mean, in this case, it is S of R, right? It is not the whole Hilbert space. So that's why I said I want to come to this later. You see, for bounded operators, you can say the representation of an algebra is basically just, you take the algebra and you map it to the Hilbert space of bounded operators. Okay.
Yeah. Okay. So yeah, my question was whether like pi of x hat.
Yeah.
This is now an operator on the Schwarz space, right?
Exactly.
Okay, so it maps not to the Hilbert space, but to like an unbounded operator on the Hilbert space. Okay.
Exactly.
Yeah, right.
So that is exactly the difference between bounded and unbounded operators. Bounded operators map to the Hilbert space. Unbounded operators map to a subspace of the Hilbert space.
Yeah, sure. Yeah,
so actually, the representation. So it's a good question, and the representation theory of unbounded operators on a Hilbert space is not that very well treated in general literature, but there is an excellent book by Schmidtgen, Konrad Schmidtgen, who is also, I mean, probably you know him because he's a professor at the University of Leipzig in the math department, and he has written a book about this. I think it's called Unbounded Operator Theory on Hilbert Spaces or so, and there is a whole chapter on that issue. So I can highly recommend it. I may also put it then in the references.
Okay, thanks.
Thank you. Let me clear our drawings. Exactly. So the point is that, so from a physical aspect, I'm trying to switch back and forth between math and physics. This is the so-called uncertainty principle. So you cannot, these commutator relations lead to uncertainty principle, which means you cannot measure an observable as precise as you want. So the uncertainty is given by the expectation value of a squared minus, is just this formula, right? And what this intuitively means is that the phase space, which was a space basically made out of points where you could reach any point, for the function f that describes the dynamics, is now replaced by a pointless state space with Planck cells. So no points exist anymore for that case. And you can imagine the replacement of the phase space, where it was, just a usual R2, by some sort of phase space that replaced the points by cells. And these cells have, the size of h bar. Okay, and the h bar is a very small constant, by the way. So it's 10 to the minus 34 kilogram meter square per second. And it's very small. The point is, if h bar would have been greater, then we would have noticed quantum mechanics in the world. Then quantum mechanics wouldn't be something that abstract or crazy to deal with. Right. What? Okay. Yeah. Maybe that is enough said about that. And now, so I mean, in a sense, explain to you the motivation. What is quantum mechanics? Why do we need, geometrical spaces or a geometrical notion of distance that does not rely on points? And now let's try to, so in a sense, give you the teaser of what non-commutative geometry does, namely replace this notion of distance by a notion of something more algebraic. Okay, and for that we give you, or I give you the distance formula in commutative geometry. Let's go through that a little bit. Sorry. Okay, so here the distance formula in commutative geometry, let's take an example. You have R, so the real line. I don't know why I'm draw. Oh, this must be from the previous. Right, so you have this, the real line, and you have P and Q. And the distance of these 2 points is given by the distance function, which is basically the absolute value of P minus Q, right? Another formulation exists for you who are familiar with Riemannian geometry. So in Riemannian geometry, the distance between 2 points, given on a manifold, is defined as the infimum of L of gamma, where gamma is a path joining P to Q, and L is so L is the length of a certain. Sorry, toilet here. So L of gamma is a path gamma joining P is commuted from the metric G. Okay, this is what we sometimes also call the Lagrangian, and this is basically the line element, we call it in physics. So G mu nu, dx mu, dx nu, where mu and nu go from 1 to d, where d is the dimension of the manifold. Okay, so you have this, you take the infimum of this, and then you have the distance function. So for example, the real line, you have R and delta. Okay, so the metric, so the manifold is now given by R and delta. And sorry. And yeah, it's R and delta, and then you just insert this. So it's delta mu nu, dx mu, dx nu. And this is equal, since delta mu nu or delta, I mean, you don't have a mu. Mu goes here from 1. So this is basically just dx squared. And, the integral of that from Q to P is P minus Q, right? So if we move on here, sorry. Are you seeing this sort of bug here? Oh, sweet. So the supremum formulation, so exactly, so there's another formulation of distances. So I gave you now a few ones, so the infimum, and there's also the supremum one, where distance on R is expressed as a primum taken over continuously derivable functions on R, okay? So you take f belonging to some continuous function that has a continuous derivative as well, and then you say the supremum over that, sorry, maybe I should, excuse me. So the supremum of f of p minus f of q, and such that f prime of x, or the derivative of x, is less equal than 1 for all x element r. So the primary objects here are observables f instead of points. Okay, this is sort of the nice thing about this supremum formulation, and that works. The advantage is does not use the concept of the path, because path means geometry, and path means metric. And in a sense, we expect in quantum geometry or quantum gravity not to have an aspect that is related to the metric. So it does not use the concept of the path, and it is thus generalizable to quantum spaces. Excuse me just a second. So are there any questions so far about, for example, the motivation or any other thing? Okay. So good. So let me, sorry, I have a bug here that is sort of bugging me. I will share the screen one more time. Okay. So, so in order to prove to you that this corresponds truly to sort of, you know, for example, in the case of the real line, that corresponds to something as a distance function, you consider here the trivial function h, which is, you know, it just maps x into x, so it's the unit function, and we show next that it corresponds to a supremum, which means that d of pq is equal to, you know, h of p minus h of q, and this is really equal to p of minus p minus q. Now, first note, so for the proof, first note that h is c, so it's continuous, okay, for r, and it has a derivative that is continuous as well, and the derivative of h is equal to 1, which is less equal to 1, which is one of the conditions that we have to fulfill for all x in R. And thus, h is in the set defining the supremum, okay? Now, suppose h is not the supremum, that then there must exist a function f, which is s, you know, from S1 of R, such that f prime of x is less equal to 1 for all x element R, okay? Sorry, yeah. This would imply that f of p minus f of q is bigger than h of p minus h of q, and this implies that f of p minus f of q is bigger than p minus q. But now, by the mean value theorem, there exists a c, a constant between p and q, such that the mean value of f prime of c is equal to f minus p, f of p, minus f of q, the absolute value of that, divided by p minus q. And thus, from the two previous equations, we deduced that f prime of c has to be greater than 1, and this is in direct contradiction with f prime of x being less equal to 1, okay? And thus, we have equality. Okay. So, so the distance on R is expressed as a supremum. We already said that. Sorry, I went back. All right. So now in the operator framework, so our approach to non-commutative geometry, in order to make the distance functions computable with operators and states, as in quantum mechanics. So you see, now we have a theory basically, or a definition of the distance, in contrast to the one that was in the infimum. That does not rely really on points, but the points are replaced by states and functions by operators. And the way to do that is the following. I just want to tell you a quick joke, sort of. Non-commutative geometry, you know, deals with or tries to basically formulate a lot of geometrical aspects without the notion of a point. And thus, sometimes it's sarcastically called the pointless geometry, which is sort of mean and funny at the same time. Okay, I just wanted to tell you. And now the point is, we define a state omega p, which is associated to each point p as follows. So omega p of f is equal to f of p. This is now our state. So it's a positive linear function. That is what the state is. And next we write the sub-expression f prime of x less equal than 0 for all x element R to make it compatible with the operator theory. Now, the way we do it is exactly by the way I showed you by taking the representation. So since X is since X hat was the, how do I say that best? So X hat was the multiplication operator basically on functions of L2, right? But, or, to be more precise, on a dense subspace of L2. Okay, and now that means that any function f can be written, so, right, and now you can take a function of this X hat, phi of X, and, oh yeah, and now the X hat here represents the representation of the original algebra. So basically, you can write pi of f of X hat or pi of X hat psi of X. And this is then just simply, phi, this thing. There, I mean, X hat and P hat are self-adjoint operators, and for all normal operators, there exists, the spectral theorem, and with the spectral theorem, you can actually do exactly things like that. That is why it is also very useful in physics. And so we can write any function, even if it's, a function of an operator, let's say, for example, I don't know, e to the power of X hat, as a multiplication on, a subset of L2. Then f prime of X less equal 1 is equivalent to saying that the norm of the commutator of d dx f is less equal to 1, okay, where this is the operator norm, okay, because, I mean, you can always take the operator norm. There is no reason to not do it. Now, the proof here is the following. Take the commutator of d dx with f on psi. This gives you d dx f psi minus f d dx psi, right? Because the commutator is just, the commutator of AB is just AB minus BA. And this gives you then, the Leibniz rule. So this acts on this. So this is basically f prime psi plus f psi prime. And since this is f psi, so this minus f psi prime, this cancels, and you have f psi c. So in a sense, the formulation of this f prime as an operator with a commutator is justified here. And the operator norm is simply given by the supremum. Let me clear this for a second. Okay, so therefore the norm is less equal to 1, and it is equivalent to that the supremum is less equal to 1, which in turn is equivalent to f prime of X is less equal to 1. Hence, finally, the supremum expression is rewritten in the operator framework as the following. So now we replaced, the point. So in the supreme, if you remember the supremum definition, we had d of pq is equal to the supremum of f of p minus f of q, such that, you have f of, f strich of X is less equal than 1 for all X element R, right? And now we replaced the f of p by this linear functional omega p of f, and the same for f of q, such that now this is less equal to 1. Thus we replaced, a definition of the supremum expression for the distance by a one that is purely algebraic, in a sense. And so here there is no there's no reference to a metric. There's no reference to any weird paths and shortest path and so on that you have to take. Okay, and that is sort of really one of the in my opinion, of course, one of the fundamentals of this theory, and also one of its main aspects of beauty, if something of that is of any value. And now we come to really what is sort of one of the main aspects since we defined now the distance function without reference to any geometrical entities in some sort of way, but rather to algebra, to elements of algebras, basically, we define the so-called spectral triples. This is the spectral triples, in a sense, are one really big fundament of non-commutative geometry, basically. Right. So a spectral triple, I will define it in a moment. Just to tell you here, it's made out of an algebra, a Hilbert space, and a derivative operator, which is usually associated with the Dirac operator. And the idea, the main concept, you know, if you take anything of what I'm saying with you, is that the main idea here is, out of this spectral triple, so out of a spectrum of an algebra and so on, I can extract geometrical quantities, you see, such that for the case or for the time that I don't have geometrical quantities to work with, I can use these triples because I know how the thing works in generality. So this is what, you know.
Excuse me, can I ask a very short question?
Yes,
you probably said it, but could you remind me what those functionals WPF, WQF, yes, how they're defined?
Well, that is a very good question. In general,
or is it okay?
Yeah, that is a very good question. It's a state, so it's basically a positive linear functional. How this is defined, that is a question for later, or maybe, I mean, okay, I don't know if I will answer to you, but you know, there's this GNS construction thing where, you know, if you have given a C-star algebra and so on, and then you can construct those states. So in basically, and you can reconstruct the geometrical entities of this this algebra. But basically, to tell you the truth, one big aspect of working, for example, on quantum field theories in curved spacetimes, you have an algebra given, and if you can construct a state which is a positive linear functional, then you can construct your whole Hilbert space and do rigorous, you know, work and calculations on that. But that is a very good question, and in general, I don't think anyone has, you know, the real answer to it. But it's an absolutely great question. I mean, here it basically just, you know, identifies f of p, sort of, because you see it is positive and it is linear because f of p plus f and so on. So this is basically that. Right. No, very good question.
Okay, thanks. I thought I have missed it, but yeah, that makes sense.
No, you haven't missed it at all. I sort of, yeah, rushed it because, yeah. So now we come to the spectral triple. So, and as I told you, from an intuitive point of view, a spectral triple encodes all the geometrical information, but in an algebraic way. And please, if you take any sentence with you, it would be maybe this. You know, the non-commutative geometry aspect of con, and especially in regards to spectral triple, is encode the geometrical information in an algebraic way. Because for the case that you don't have the geometric information, but the algebraic information, you plug that in, and then you should be able to obtain the geometrical one. Of course, it's not that easy and straightforward. You know, it's not a formula that is, I mean, in non-commutative algebra and geometry in general, everything seems to be always very hard. But that makes it probably interesting. Okay, so let me give you an explicit definition of this spectral triple. A spectral triple is given by A, H, and D. And so by an algebra, a Hilbert space, and some derivative operator, which is a self-adjoint operator. So it is composed of a unital C-star algebra. And I just noticed I didn't define what a C-star algebra is. Okay, please write in the chat who of you know the definition of a C-star algebra, or are sort of familiar, or who isn't maybe. That would be the more important question. Okay, perfect. Perfect. Remember this, yeah, I don't know. I mean, I will define everything from the very beginning. Here I just give a general teaser aspect, but then we will go really more rigorous and rigorous. So don't be intimidated right now. I will just give you the very definition, and then we will go very clear into, you know, the introductory definitions of all that. So and while I'm on it, how familiar are you? So is anyone not that familiar with Hilbert space or Hilbert spaces? I mean, not everyone has to be, of course. I got a lol for my pointless geometry joke that I am seeing right now. That is nice. So okay, so I will go in more detail. The point is, so as I said, you have an algebra, some algebra, which, okay, is a unital seesaw algebra. I will explain in more detail what that means. You have a Hilbert space, and you have a self-adjoint operator D, which, you know, is a Dirac operator, or some sort of operator with a compact resolvent, such that the commutator of D with A is bounded for all A element A. That is the crucial aspect here. And in this context, if you have two states, sigma and sigma prime, their distance is defined by the supremum of A element A of the, you know, mean value of sigma A minus sigma prime of A, for the case that the norm of the commutator of dA is less equal to 1, because this is basically what bounded means, modulo a constant, right? Okay, just to give you a very easy example, okay, for which you don't need to know a lot actually. The example of a Riemannian manifold. So you know what a Riemannian manifold is. I guess many of you, probably most of you, know it better than I do. But so you have, let's say you have a compact Riemannian manifold, okay? So it means that your functions are basically all very well defined and so on. And a spectral triple on this Riemannian manifold is defined in the following way. The algebra, so what is a spectral triple again? Let me mark this here. So a spectral triple, as I said, is algebra, Hilbert space, and Dirac operator, right? And right, and the algebra is basically just the algebra of the continuous functions over that manifold, okay? So you don't, right, you don't take any, so it's nothing fancy, you know, just the algebra of the continuous functions. So you have a continuous function, and so what is an algebra? An algebra, you know, is some set such that you can multiply their elements and they stay in that set. You can add their elements, they stay in that set. And an algebra over a ring, you can take elements of the ring, multiply it by elements of that algebra, and it stays in that set. Basically, that's all what an algebra is. So I will give a more, you know, precise definition in a second. But the point is, what does it mean, or what is important? You have f of x and you have g of x, okay? And they're both continuous functions on this manifold that is compact. Now, if I add those two continuous functions, I will get a third function that is continuous. And if I multiply those two functions, right? So this is f of x, g of x. I will also get a function that is continuous. You can actually, this is a very nice exercise to prove why f of x times g of x is continuous if f of x and g of x is continuous. This holds, of course, also for non-compact manifolds, but this is not that very important. So in a sense, you have, so instead of looking of the geometry, you know, instead of looking on the geometry of those objects, what you look at is the algebra that they form, and this is sort of what is replaced in non-commutative geometry. So in non-commutative geometry, you have, you know, instead of working on the manifold, you work with the algebra over that manifold. And as the Hilbert space, you choose some L2, so square integrable differentiable forms, you know, i.e. elements acting on by pointwise multiplication on H, as I explained to you before. And the choice for a first order differential operator is the Dirac operator, because the square of that operator or not because, but that is a very nice property of that the square of the Dirac operator gives you the Laplacian, okay? So, and then you have your spectral triple, basically. And for you who still remember the introductory course in differential geometry, the Laplace-Derham operator satisfies the following. There is delta. So delta is d times delta plus delta times d, where d is the exterior derivative and delta is the exterior co-derivative. And with this exterior derivative, you can build forms. Okay, so so basically, I mean, I don't know, it's gonna even be recorded. I'm not very sure. So okay, take some vector space, right? I don't know, call it X. Okay, you have this vector space, and you have functions over this vector space. Now, if you take the derivative, the exterior derivative on elements of this vector space, basically you go from X to omega 1 of X, right? So the one forms. Okay, so basically, let's say you have an element of X which is A, then dA is a one form, and in order to get a two form, you take omega 1 of X and wedge it with omega 1 of X, and that is how you build your n forms. And one aspect which I hope we will reach in the next lecture, probably, no, not probably, most definitely, is, you know, in non-commutative geometry, is forget about the vector space and deal with the algebra. You take the algebra as your zero form, and then by defining, and how that will, you know, happen, we will see then, because that is a little bit more complex. But in general, the idea is the same. You take an algebra and you define an exterior derivative, and this exterior derivative gets you the one form. And in order to define a two form there, you just wedge, I mean, in a sense, you just tensor in an algebraic way the one forms with each other. But okay, this I'm going already way too far, so more far than I wanted. And so, as I told you here, the exterior derivative, you know, you have vector space, and it takes you from functions of this vector space to one form. And so with the D, you can basically always go, and they have very nice names. Okay. Now, the point is, these are what do you call this? Null potent, which means that if you square them, it is equal to 0. So that means, and from that it follows that D is equal to D plus dy, because if you take D square, this is D square plus delta D plus D delta, right? Plus delta square, because because D and delta do not necessarily commute, and in general don't. And since this is 0 and this is 0, you end up exactly, you know, with the Laplacian that we defined. Good. Okay. Okay. So now the distance between 2 points P and Q, considered as pure states, omega P and omega Q, is given by the supremum norm, as we did it before. So omega P of F minus omega Q of F, and such that the, you know, commutator D of F is less equal than 0. And this is, in a sense, the generalization of the previous formula on R. And one can recover the metric from this definition, although it is not present in this definition. And in a sense, the Dirac operator encodes the geometrical information of the metric. Okay, so this is sort of, yeah, that was the teaser, sort of, just to get you, you know, interested. And right. So let me see. Okay. So, as I said, the general idea of non-commutative geometry is to shift from topological spaces to algebras of functions defined on them. So next we'll give definitions and facts about algebras and functions on topological spaces. And this is, you know, exactly such that, I mean, such that I'm going to go through all definitions with you. So just that you have, you know, in a sense, sort of, aspect on how these things look. Right. Sorry, before I continue, are there any wishes that regarding my style or something that I can oh wait, Maximilian. Yes, it is exactly that the resolvent said. I will define it in a second, okay? But thank you for the question. So, right, with a compact resolvent set. Oh yeah, you're right. I didn't. It slipped. It slipped my mind that I used here the resolvent. Thank you very much for this clear question. I will define it in a second. Is there any other wishes? Do you want to go faster, slower? Just like communicate with me. Okay. So, okay, we go here through a few definitions, basically. We define an algebra. So what is the definition of an algebra? I gave it to you, previously, but let's say an algebra with a field of complex numbers C. All right, I said a ring. I don't know why I said a ring. I meant the field. Is a vector space over C such that the objects like alpha A plus beta B with A, B element A and alpha beta element C make sense. Okay, in a sense, you can, there's a product. There's you can add them. You can multiply these constants with them, and it's still in A. And there's a product. So the product takes an element of A with an element in A and maps it to A, and it is distributive over the addition. It is also associative. Well, it doesn't need to be, but in general, I will only work with associative algebras. So distributed means A times B plus C. So some product, whatever that product is, so it's not just the pointwise product. But of course, if you work on a function space that is commutative, you have, so if you take the algebra of functions over some commutative manifold, this is the pointwise product, basically. And A plus B times C is AC plus BC, where A and B and C are all elements of the algebra. And in general, the product is not commutative. And this is exactly sort of the jumping point, they say, the skipping point, or the important point in in these frameworks. So, well, we mostly work with unital algebras, but in general, it doesn't have to be. So unital algebra is an algebra that has also the unit element as an element of that algebra, which means you can multiply it with that element, and so A times 1 is so it's the 1, basically, right? So an algebra A is called a star algebra if it admits an sorry, I just need to check the chat. So an algebra A is called a star algebra if it admits an antilinear involution star, which maps A into A with the following properties. If you take the star of the star, it is equal to A, okay? A times B star is equal to B star A star, and alpha A plus beta B star is alpha complex conjugated times A star plus beta complex conjugated times B star. Okay, so the bar denotes here the usual complex conjugation. So, I mean, I will give you examples later, but take, for example, the matrix algebra, okay? Matrix algebra of 2 cross 2 matrices over C, over the complex numbers. And there, the involution is just, the complex conjugate, what you call it, right? Okay. Next we define, so that was, we define an algebra, now we define the star algebra, and now next we define a normed algebra. And a normed algebra is an algebra with a norm, okay? Well, it sounds like a very trivial definition. Basically, so you have an algebra that fulfills all your nice properties, and in addition you have a norm. And a norm, is is a function such that it is what a norm defines, right? So it's greater equal than 0 and only 0 if a is 0. It is such that the norm of alpha times a is equal to the mean value of alpha times the norm of a, so you can take the a out sort of, and the norm of a plus b is less equal to the norm of a plus b plus the norm of b, and a times b is less equal to a times the norm of b for any a, b element a and alpha element c. So I was a little bit younger than that, than today. So actually, I was also a PhD student at the Max Planck Institute, and I was, I was learning functional analysis, and I saw these definitions, and they were very clear to me. And then I had to prove that it is the case, and I had extremely difficulties. And then I figured it out, and then I started inventing norms. Okay, just for the fun of it, just to see if they fit. It's a nice example to put for yourself, sort of. The topology defined by the norm is called the norm topology. Okay, so the corresponding neighborhoods of A are given by B element A if the norm A minus B is less equal to an epsilon. So there is a topology defined for these operators or for these algebras as well. That is basically what is important here. And there you have a Banach algebra. Banach algebra is a normed algebra which is complete in the uniform topology, which means that all Cauchy consequences, Cauchy sequences converge in that norm. And Banach star algebra is a norm star algebra which is complete. So A star is, and in addition, A star is equal to the norm of A star is equal to the norm of A. And now a C star algebra. So a C star algebra is a Banach star algebra whose norm satisfies in additional the identity that the norm of A star A is equal to the norm of A star for all A's element A. And the point why C star algebras are very nice is that especially in physics, we have observables. These observables are given by self-adjoint operators. And these self-adjoint operators are usually unbounded, but if we, exponentiate them, then they, in a certain way, then they become unbounded, bounded, and they form sort of a C star algebra together. And with C star algebra, there are very important results, as I mentioned, the GNS construction theorem and so on, that make them very useful in day-to-day life, so to speak. Right. So this. I hope my quick sort of introduction to these things made the definitions easier. Now, so I will give you a few examples. Just what the hell did I just define in a sense? So the commutative algebra C of M of continuous functions on a compact Hausdorff topological space. Okay, so this is an example, with star denoting the complex conjugation and the norm given by the supremum norm. Okay, so the space has to be compact because otherwise this can explode, right? So this is the supremum norm, and this defines you a C star algebra. Okay, right. Now, if M is not compact, you take the algebra C0 of M of continuous functions that vanish at infinity, right? So if M is not compact, then then you have trouble with defining this supremum norm, of course. So a nice exercise. I mean, I don't know how invested you are in this Ringvorlesung, but if you have time and you have 10 minutes to spare, sort of. You can prove that this example is truly an algebra and especially a C star algebra. Okay, another nice example of so what I should also mention is here you have a commutative algebra, right? This algebra is a commutative algebra. Okay. This algebra is a commutative algebra, right? because f of x times g of x, okay, for functions, you know, continuous functions, actually continuous is not even that important, is equal to g of x times f of x if this multiplication is the pointwise multiplication. But in general, this doesn't have to be the case, right? And maybe let me say, mention here one example of a very nice non-commutative algebra. Maybe I will mention it later, but just because it fits here so nice. So you say, well, okay, give me the commutative algebra over continuous functions. How does a non-commutative algebra over these continuous functions look like? And then I give you a product. Okay, it's basically just in the product. The product, let's say f star g of x, or no, let's define it a little bit different. Sorry. Okay, let me define it that way. F of x times g of x is given as e to the power of 1/2 theta ij di dj. Well, I could write it like this. And dj g of x, okay, where f and g are now an element of that. So this is a product, okay? So this is the derivative with respect to x, and this only, you know, this is an exponential function. You can represent it as an integral. It has very nice integral representation. But it, I mean, in this way, you know, a hardcore sort of mathematician who brute forces everything knows what it means. It means I have an exponential, I can do a Taylor expansion, and the di acts on f of x, and this dj acts on g of x, and theta ij is some skew symmetric matrix, okay, and constant matrix. So it's theta ij. It's just a, you know, symplectic matrix if you want. And I and j go from 1 to 2, let's say. In that case, this is just the epsilon tensor times some constant, and this constant is what they call a deformation constant, because if this constant goes to 0, okay, if theta goes to 0, so this product is usually denoted by star theta. So in the limit theta goes to 0, f of x star theta g of x go to the pointwise product, okay? And that is what is sort of the nice thing about these things. You can go from one to another, and a lot of, you know, fundamental physical theories can be actually understood as a deformation, is what this is called, of classical theories. But okay, so take this product, this non-commutative product, and then you will see that, you know, for continuous functions on a compact manifold, that this will still give you, you know, an algebra. So if you multiply 2, they will still be a continuous function, and so on, even with that product. Okay, that was just a little bit of a... Okay, now, so the non-commutative algebra, so an example of a non-commutative algebra is, and one in which is very important, by the way, is the algebra of bounded linear operators on an infinite dimensional Hilbert space, right? So, right, so you have a bounded linear operator means, on a Hilbert space means you have a norm on this Hilbert space, which is given as a supremum norm, and this supremum norm is finite, okay? So the non-commutative algebra B of H of bounded linear operators on an infinite dimensional Hilbert space with the involution given by the adjoint, and the norm given by the operator norm gives you a normed C-star algebra, well, a C-star algebra basically, so a normed star Banach algebra that is complete. Okay, and a very, you know, a sort of particular case of this example is, as I mentioned before, also the non-commutative algebra given by n cross n matrices on the complex vector space, and where T star is a Hermitian conjugate of T. So you have a matrix and the conjugation, which is important, as you see here. To make an algebra a star algebra, you need some sort of operation which you know, defines you the involution. And right, and this is just the Hermitian conjugate of T. And the norm, there are many norms, and it's a very nice, I think in linear algebra you already do that, is to prove that many of these norms are equivalent by showing, you know, some certain inequalities. And so the norm of T is the positive square root of the largest eigenvalue of T star T, okay? So, I mean, T star T is a self-adjoint operator, a self-adjoint matrix. And if you take the positive square, so, I mean, you can calculate for that matrix, the eigenvalue equation, and then you take the largest eigenvalue and take the square root. Basically, that's all there is to it. All right. Right. Okay. Now, so I gave you some examples of C star algebras and algebras in general, of commutative ones and non-commutative ones. And they're very, I mean, it's a beautiful theory with incredible many results that are mind-blowing once one understands what the hell they're talking about. But so it's really, I mean, it's really something else, these theories. So I recommend anyone to read about C star algebras in general, just to get a sort of general idea of what is happening there. Another definition that we will use, maybe not that often, but I will still bring it in, is the definition, the notion of an ideal. So a proper norm closed subspace I of the algebra A is a left ideal, respectively a right ideal, if A is an element of A and B is an element of this I, imply that A times B is in I, okay? Respectively right ideal if B times, so if A is an element A and B element E, such that B times A is an element I. A two-sided ideal is one which is both, so it's a left ideal and a right ideal. And the ideal I is called maximal if there exists no other ideal of the same kind in which I is contained, okay? So that is an ideal. Ideal means, okay, I have an algebra, I have some elements of this algebra, and now I have a subset of this algebra, a subspace of this algebra. I take those elements, I multiply it with the algebra, and they stay, you know, in this smaller sub-algebra, because the ideal is also a sub-algebra. Also a very nice, you know, example if you want to calculate it. And now to the question of Maximilian is the resolvent set, and sorry, of I said Maximilian, is it true? Or was it Marcus? No, it was Maximilian, perfect. So, sorry, things annoy me. Okay. The resolvent set R of A, so, right, so let me define what the resolvent set means. Of an element of an algebra is the subset of C such that lambda is an element C and A minus this lambda element of C is invertible, okay? Where, you know, this is the one in C. And for any lambda element R of A, so A minus lambda I is called the resolvent of A at lambda, okay? So that is the resolvent set. Now, why is this resolvent set important? There is actually a lot of work on the resolvent set and a lot of very interesting, important theorems on it as well. What I actually, well, I mean, for those of you who are familiar with the Weil algebra, the resolvent algebra, which is basically the algebra made out of these resolvent sets, is a very nice sub-algebra to it, okay? And or basically you can do a lot. What you can do with the Weil algebra, you can do with the resolvent algebra to a certain extent. And actually you can even do more, and this is still subject of current work. But I mean, in general, why we need it is that the complement of this resolvent algebra, or sorry, of this resolvent set in C is called the spectrum of A. What does the spectrum mean? This, oh, I wrote it here in a German way. So the spectrum for any element of a C star algebra is the non-empty compact subset of C, okay? So okay, so you take the resolvent algebra, okay, and the complement of that resolvent set or resolvent algebra is the spectrum, okay? And what is nice about C-star algebras is that the spectrum for any element of these algebras is a non-empty compact subset of C. Now, the spectral radius of A is given by the supremum of lambda element of Ri. Right, so that's the spectral. And if A is a C-star algebra, this spectral radius is just a norm. And what is even nicer is when this element that I'm looking at is a self-adjoint operator or a self-adjoint element, right? So an element A is called a self-adjoint if A is equal to A star. And well, I mean, yes, I mean, for an algebra, this should hold. You know, I mean, the point is for bounded operators. So for a matrix is called self-adjoint if A is equal to A star, right? But for unbounded operators, this is a little bit more complicated because as the discussion before, you have to take care of the domain, basically. Okay. And the spectrum sigma of A is, so for a self-adjoint operator is real. And that is basically what makes self-adjoint operators, especially in physics, so important, because at the end of the day, you want to measure a number, right? A number means a real number. So with a complex number, we cannot do that much. But a real number, which means, I don't know, you measure the temperature, right? Temperature is a real number. Now it's, I don't know, my room, it's 24 degrees, 24.9 degrees. Okay, this is the number. And in order for an observable, you know, in quantum mechanics, to have a real spectrum, it has to be self-adjoint. So a real spectrum of A means that A is self-adjoint, and that means it's basically the spectrum is a subset of the interval minus norm of A to A. Okay, on sigma of A square is a subset of the interval 0 to norm of A square. What is, so, okay, maybe what you only take with you from here is self-adjoint element of an algebra means I have a real spectrum. Now, if A is an addition to, or is self-adjoint and it is called positive if the spectrum is a subset of the positive half-line, okay? So A is positive if and only if A can be written as a product of B star B for some, you know, arbitrary element B in A. Okay, so I know this is a little bit, well, we say in Austria, zach, which means like a little bit boring, but these are definitions nevertheless, and I think it's nice to have them there. You know, in any case, you can always look them up. Now, a star isomorphism between two C-star algebras. So, okay, basically all the definitions I give you, I will use later on, okay? So please apologize the massive use of them. So a star isomorphism between the C-star algebras A and B is any C linear map pi, which maps the algebra A to B, satisfying, so the algebra A to the algebra B, satisfying pi of A times B is equal to pi of A times pi of B, where the product here, so in general, the product here and the product here do not have to be the same, right? So it's a star isomorphism or a representation as well, which we will define in a second, if PA of star is equal to P of A star. Yes.
I have a very quick question. Do
yes,
we
please.
require it to be invertible in some sense, or because we call it an isomorphism?
Right. Yes, it has to be right. I'm sorry, this should have been written there. Yes, it has to be invertible, and right. So yeah, you're right. This should. I think this follows nevertheless from this definition. There are a lot of equivalent definitions, but yeah, you're right. This should actually. So there should exist an inverse that basically does the same, and I think you can get that out by taking pi inverse of this one. Yeah. And now we come to the most important thing. So what I was telling you before, I was saying to you before, for an unbounded operators, and this is the last definition before we close this session. So let me give it to you now for bounded operators, and C-star algebras are made of bounded operators. A representation of a C-star algebra A is a pair, H and pi, where H is a Hilbert space and pi is a star morphism, between A, so the C-star algebra A, and the C-star algebra of bounded operators on the Hilbert space. In addition, the representation H pi is called faithful if the kernel of pi is the zero space, is the null space. In the case that you don't have a C-star algebra, by the way, you would have H, pi, and D, where A is, right, so where pi is a map between, is a star morph, or yeah, actually, it's, well, no, there's also a little difference there. It's basically a mapping between A and, you know, some dense subspace of H. Okay, that would constitute then in for the unbounded case. Okay. Right. Okay. I think this is a good stopping point. I hope I didn't, you know, suffocate you all with all these definitions and so on. But I mean, it's important, so that, because in later I will sort of explain the following, and maybe I will put it now very precise. You have an algebra, you have a given algebra, you have a Hilbert space. So an algebra given on some function space, for example, you have a Hilbert space that you define, and then you have a Dirac operator or some derivative operator. By taking those three, you can reconstruct the underlying geometry of the space. And how to do that, in order to do that, and how to do it, all these definitions come into play, okay? So that's maybe why they're important. But yeah, so I think, yeah, I should end this session for today. Are there any other questions so far? No, and I mean, oh, I hope not, because I mean, I think I would have to prepare. No, I think, I mean, look, the general idea, as far as I remember it, and I talked with your scientific coordinator, Jörg Lehnert, about it, is it's sort of a little bit unfortunate that we always go, you know, you do your PhD in something, and then you remain in that area, and you don't know, in this, you start forgetting slowly all your other stuff that you learned in your math studies or in your physics studies, and you don't see general pictures of things. And I think that this Ringvorlesung was really in the spirit for you to see a general, you know, idea of what goes on beyond your subject or area of expertise, just to get a general idea. I don't think there will be an exam, and I don't think there is an exam, no. And I would definitely do all in my power to avoid that as well, because I would have to write it and I would have to grade it as well. And I don't think, you know, now it's also not fair. I mean, with 3 sessions, yes. Any other questions, remarks? Well, if not, then I thank you all for your attendance. I hope, you know, you can take something with you. And we see each other the next 2 Fridays. Until then, I wish you a nice weekend.
Goodbye.
Bye. Take care.
Bye.
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 Bye.